Hello, my name is Dmitro, and today me and my two colleagues, Denis and Dmitro, would like to present to you our project called Ucuddle. It's a search engine, and our supervisor was Vyacheslav Shevchuk from a Dialog Semiconductor company. The project's main objectives were to develop a search engine capable of indexing public websites and enabling fast searching. Ucuddle has the following functions. It is implemented in a concurrent and parallel fashion to maximize the usage of resources of different computers. We have enabled easy scaling because our system should be able to support large number of simultaneous requests. It was our requirement that we needed to keep up with. And the next point was to enable safe communication between components and to secure our servers. We have collected at least 5 million web pages in our database, and we have enabled searching in this large data collection. So our development was divided into 8 stages. Here is an overview of these stages, but we would like to tell you about each of the stages in more detail. So the general concept of our system is the following one. We have three subcomponents. It is crawling and searching, which are independent of each other, and storing, which is the database where all of our data is being stored. When users go to our website and send some requests, they go to the searching components, and they pass through our load balancing engine X. It balances the loads between our web processes, which perform search in our database, which is Elasticsearch. Besides this, independently runs the crawling process, which consists of the task manager that determines which process should parse which pages, and the crawlers themselves. And now we would like to tell you more about crawling, and Dima will tell you about it.
So our crawler written in Go language is concurrent, which was achieved by using coroutines, the tool of the programming language. They are also known as green threads. The communication in them was organized via Go channels, with which acted as concurrent safe queue. Also, important thing to mention is that our crawler supported robot.txt, so that we ensure we didn't parse the data which the owners of the website don't want us to parse. The crawling was done recursively. The entry point of each recursion was the domain of the site, from where parsing continued to its child URLs and so on. To be sure not to make infinite recursion on each step, we checked whether the page was parsed before by O1 check, as it was quick enough not to waste much time on it. Also, we benchmarked our crawler by multiple runs with different parameters and configurations on different machines, and then analyzed the results that we got. This is the first version of it. On the vertical axis, there is the speed of parsing in domain per second. On the horizontal axis, the number of coroutines or green threads. Because of consistent growth on this graph, we weren't able to make any conclusions, so that we expand the number of coroutines scale, and got this graph, and recognize that after 1,000 coroutines, there is no significant growth, so that we picked it as an optimal value. Yeah. On other numbers of CPU cores, we discovered that 500 is enough. And then we set those values for the deployment stage of the project for the most efficiency of the work.
And the next part of our system is searching. So let's go to it. And our search concept is the next. Our search is based on 5 million pages of Ukrainian registration domains with UA extension. And when we analyzed these domains, so we find out that approximately 50% to 50% Ukrainian and Russian web pages. So these two languages became the main in our system. So how does user interface work? User go to our search page and make its search query. After we analyze the language of this search query and look for in our database among web pages for this specific language. For such search in this query in database, we use such function as full text search in our database. But for this, we also should set up special analyzers for specific languages. And in general, analyzers, this is special settings for a language to say our database how it should make this full text search for this specific language. Next slide. Also, great part of our project was own implementation of PageRank algorithm. And in general, PageRank is an algorithm which is used by the Google to rank domains in the search engine. We also want to add this algorithm to our project, but we understand that it is a really difficult mathematical task. So we decided to create it as a part of our semester project for linear algebra course. So we read scientific articles and wrote a paper about this algorithm. And also a link to this paper you can find on this slide in our presentation. Also, we created a working code and created a graph of 44,000 of vertices and 140,000 of edges, made a sparse matrix and calculated the page rank for each of the domain. And such, we ranked 112,000 of pages. Next slide. And let's go to the last part of our system, which is storing. And we use Elasticsearch database, which is a distributed search and analytics engine. We use it for saving data and quickly search for them. And the main feature of this database is full text search, which is used to search user queries. And on this slide, you can see the biggest company which is used this database, which proves that this database is a leader on the market in its sphere. So next slide. And we also decided to speed up Elasticsearch because we have a problem that even with a small data set of less than 200 megabytes, the search took a long time. It was a really great problem because we know that Elasticsearch can show really great performance even for terabytes of data. So we decided to fix it and start to analyze logs and read different articles and researches and find out several great advices for us. And first of all, we increase the number of shards. In general, Elasticsearch is split on indexes, where index is a collection of documents which is combined with special logic, with settings and mappings. Also for index, we can set up special number of shards. And in general, shard is a separate thread which is used for searching and indexing. But when we set up really great number for approximately 100 shards for 4 nodes of Elasticsearch, it's really great number, and it can have less performance than even 3 shards. So we should research this topic and find out that the value of 3 shards is optimal for our configuration. The next advice is increasing GOM heap size, and such we make longer pauses between garbage collector. And the last great advice is creation cluster to use power of multiple computers. Next slide. And now I give my word to Dmitro.
Thank you, Dennis. And now we have talked about all of the parts of our system. We have talked about crawling, searching, and storing. And now it is the time to summarize all of it and tell you about the cloud deployments of all of this, all of these programs. So we have used two cloud platforms, namely DigitalOcean and Linode. We have also used on-premise server, and we have in overall we have selected more than 10 computers, 10 virtual machines, and we have configured them to run our different programs and communicate with each other. Of course, this involves a lot of configuration, and it would be very painful to do the configuration manually. That's why we have used the Ansible utility tool to automate the deployments and the server configuration. We have created 6 playbooks for SSH hardening, for needed software installation, primarily the Docker and Docker Compose. We have also created playbooks for IP tables configuration to close all unused open ports. We could do it, we started doing it with firewall, but firewall seems to be in conflict with Docker, and this was our solution to solve it, well, to use IP tables. And the last playbook was the installation of monitoring utilities. And the use of Ansible allowed us to have a very straightforward and a quick deployment pipeline that consists only of 3 steps. The first step is building all images. The second one is uploading them to Docker Hub. And the last step is just to launch the Ansible script corresponding to the needed container that we want to deploy. And that's it. Everything runs automatically. We have also configured the load balancer Nginx. One of this tool's objectives is to cache the static files, but we had another usage of it. The problem was that our servers are vulnerable, and some ports do not have the authentication needed, so everyone on the internet can access it. So we had 2 solutions: to create a private cloud, which is a little bit difficult and expensive, and the other solution, which we have chosen, was to put a proxy before each process that would perform the authentication. And this was our solution, and we have secured all of our processes, almost all of our processes, with basic authentication with Nginx. Now, this was our initial system. As you can see, our task manager had open ports to everybody on the internet, which was not great. And we have solved it by putting in front of it the Nginx proxy server. Here is the Nginx, which is performing the load balancing. And in front of the web application, there is also Nginx for caching and for securing. And the third scheme, as you can see, it concerns the database, Elasticsearch, which in previous scheme was just a single node. And in the last improved system, it consists of 3 nodes. We have developed our code to be asynchronous, and our first implementation was based on Flask framework. And as we know, Flask is only synchronous, which was slowing our web application. We had a very heavy input-output task, which was the database communication. And that's why we have solved this problem by switching the framework from Flask to Fast API, where all of the roles are asynchronous out of the box. They enable concurrency. We have also launched several threads with Uvicorn and Event Manager G-Event. And in that way, we have utilized both concurrency and parallelism. Um, we also needed to make some tests to see whether all of our suggestions and improvements made sense. And we have used the Gatling program for that. We have written the scenario of our website usage, and we have launched this scenario for 1,000 simultaneous users. And when we launched our first test, we got more than 30% fails, which is not a great result. And after switching to Fast API, the number got reduced to 25%, still a lot. But after we switched to Elasticsearch cluster, it greatly improved performance, and we got only 6% fails. Um, we have also mm, um, we have also seen that the cluster loads was growing. That means that um, our bottleneck was the cluster, was the database, and the solution of scaling the system lied in the cluster improvements and in cluster enhancements. So the final conclusion was: so if we want to increase the performance, we need uh, to rent more machines for our Elasticsearch, more data nodes. The statistic is as following. We had a 4-node cluster with 8 virtual machines for crawling processes. We had 39 total hours of parsing. We have parsed almost 5 million websites and collected almost more than 400 gigabytes of data. The average parsing speed was around 112,000 pages per hour. Now let's look at the demo of our platform. Here you can see our search engine, and it only works, as we have mentioned, in Ukrainian and in Russian languages, because we have concentrated our parsing processes only on this part of internet. So let's look for example, our university where we are studying. It is called Ukrainian Catholic University. And let's see what results we have. So our first page shown here is the official website and some news of our university. Let's look for the weather in our city. Here we have some propositions where we can look for the weather, and so on. Now you can also star our GitHub University and track our progress. Thank you for your attention.